Hello, my name is Sander Kamps and I am presenting our work on assessing the quality of evolving Haskell systems by measuring structural inequality. This work is a collaboration between Bastiaan Heren, Johan Juring and me, all from the Open University in the Netherlands. Our work focuses on establishing a means of determining the source code quality of Haskell systems. And the importance of high-quality software is ever increasing. But still, in contrast to many other programming languages, the source code characteristics that influence the quality of Haskell systems is still largely unknown. As of yet, there has not been any research done on the evolution of the software structure with respect to software quality and consequently the defect proneness of Haskell systems. We have performed an empirical research to ascertain whether structural degradation is related to decreasing software quality. Software quality consists of multiple attributes, and these can be divided into internal and external quality attributes. Examples of internal quality attributes are volume, cohesion, and coupling. Internal quality attributes can be measured directly by using metrics such as the log, LCOM, and CDO metric. And from these, the external quality attributes such as modularity, maintainability, and security can be derived. In our research, the log, LCOM, and CDO metrics are used to measure the size, cohesion, and coupling of Haskell modules. The log metric is defined as the number of lines of source code, excluding comments, white space, and empty lines. In this example, you can see 5 lines, of which 2 are empty lines, 1 is a comment line, and 2 lines contain code. In this case, the log value is 2. The LCOM metric counts the number of disjoint sets of functions contained within a single module. In this example, there are 6 functions, of which the function f, g, and h form a set, the function x and y form a set, and the solitary function a forms a set. In total, this results in 3 disjoint sets. The CBO metric counts the number of other modules a Haskell module imports. In this case, module A imports module B and C, and therefore its CBO value is 2. Now, the information on this module level can be very useful in certain situations. However, in other situations, the need may arise to get an indication of the software quality on system level. And then, preferably, as one figure that describes a certain quality aspect of the entire system. And in these cases, the metric values must be aggregated. 2 popular aggregation methods are the mean and median. These methods are reliable methods to determine the central tendency when the metric distribution follows a Gaussian distribution. They are simple to calculate and can be applied in the same way for all types of metrics. However, when the distribution is skewed, they lose their ability to reliably indicate the central tendency, as can be seen here for both positively and negatively skewed distributions. As a matter of fact, software metrics are generally highly skewed, as this graph clearly shows. And here we can see 2 software metrics that both have a positively skewed distribution. So these 2 methods, although often used, have a clear disadvantage when used for aggregating software metrics. An aggregation method that can be reliably applied to skewed distribution is the Gini coefficient. The Gini coefficient is a measure of the inequality in the distribution of values within a certain population. One of its applications, for instance, is to determine the wealth distribution in a country. And since a couple of years, research has been done to determine whether the Gini coefficient can be used to function as an indicator of software quality. This research, however, has been done for object-oriented languages and not for functional languages, such as Haskell. In our research, the Gini coefficient is applied to the log, LCOM, and CBO metric populations of Haskell modules. A disadvantage for using the Gini coefficient with regard to our research is that it is unable to make a distinction between systems with all equally low quality components and systems with all equally high quality components. Take as an example a very contrived system that is composed of one module containing 100 lines of code and another system that is modularized into 10 components, each of which has 10 lines of code. So I think we can all agree that the second system is of a higher quality than the first. However, the distribution inequality is the same for both systems, in this case 0, which means that both systems' populations have no inequality. The Gini coefficient has a range from 0 to 1, and 0 indicates a perfect equality and 1 indicates a total inequality. A possible way to mitigate this disadvantage is to combine the outcome of the Gini coefficient with a traditional method such as the mean or the median. The requirements for combining both methods is that they both have the same range and scale. This means that the traditional method needs to be adapted so that its range also runs from 0 to 1. And to achieve this, we have developed the ideal value deviation function, which we abbreviate to IVD. This function evaluates to a result from 0 up and including 1, depending on the deviation of its input from a certain ideal value. And the input of the IVD function is the result of the traditional aggregation method. The function parameters are, as part of the research, empirically determined, and we have determined a lower bound, an ideal value, and an upper bound. So, when a system's aggregated metric value falls between the bounds, it will receive a score going from 0 up to 1, depending on its deviation from the ideal value. We have parameterized an IVD function for the module size metric, the module cohesion, and the module coupling metric. And to illustrate the use of the IVD function, this image shows a graphical representation of the IVD function. Let's say that the lower bound is determined to be 5, the ideal value is set to 10, and the upper bound is 15. An input of, for instance, 7 is between the lower bound and the ideal value. And in this case, the upper part of the equation is performed and the result is 0.4. So the result will always be a value between and including 0 and 1. Finally, the results of the Gini coefficient and the IVD function will be combined by multiplication. Note that we use the complement of the Gini coefficient, we call CG, to align it with the outcome of the IVD function. This means that the Gini coefficient result of 0 now indicates a maximum inequality, just like the IVD function result of 0 means maximum deviation. And when the aggregated metric values of multiple releases are plotted, an image occurs that shows the evolution of that specific quality attribute over time. In this case, the complement of the Gini coefficient for the module size metric of the open source project Panda. In the same manner, we can look at the number of post-release defects per release and use this to ascertain whether the aggregated metric value gives an indication of the software quality. If a quality exists between these two, this indicates that a change in default proneness of the source code relates to a change of the aggregated metric values. Taking a look at the corresponding scatter plot, we can see that when the CG value increases, meaning that the mutual differences in module size decreases, the number of post-release defects drop. For our research, we have measured this correlation for 3 popular open source Haskell projects, this being Cabal, GHC, and Panda. Our research objectives are, first, to determine the parameter values of the IVD function for each of the 3 metrics, and second, to ascertain whether structural degradation in the form of an increasing modular inequality is related to a decreasing software quality as determined by the growing number of post-release defects. And therefore, we have formulated 3 hypotheses, being 1, the distribution inequality of each of the software structure-related metrics LCOM, CBO, and log is correlated with the number of post-release defects. And 2, combining the distribution inequality measure with the IVD function increases the strength of the correlation with the number of post-release defects. So here we test whether combining the Gini coefficient with the more traditional method compensates for the weakness of the Gini coefficient to distinguish between systems with all equally high quality components and systems with all equally low quality components. And then the third hypothesis, the distribution inequality measure can serve as an indicator of structural shifts. So, to determine the parameters of the IVD function, we have analyzed 135 Haskell systems and used these to build our baseline sample set. We have developed a Haskell application to statically analyze Haskell source code, and this application is open source and available on the following link. And this link will also be shown on the last sheet. We have used the reverse dependency list to select all Haskell systems on which at least 100 other Haskell projects depend. And this is done to obtain software that is deemed of high enough quality by the Haskell community itself. And as we use this sample set to derive a benchmark, the IVD function, against which a system will be evaluated, it is important that the included Haskell systems are proven to be reliable. Mining the repositories and subsequently analyzing the data is done by performing the following automated steps. First, the project to be analyzed is cloned, and then for each project we analyze the source code and determine the metric distribution. So this is the distribution of each of the 3 metrics. And third, the analysis results are written to file. These steps are executed automatically 135 times. And finally, the data is loaded into the statistical analysis software R for further analysis. And on the basis of this data, we determined the lower bound, ideal value, and upper bound for the IVD function per metric. And to illustrate the metric distribution, we show the histogram of the modular size of the sample set. Now, we've chosen the IVD parameter values such that it reflects the distribution of the sample set, and we can distinguish between systems with a decimal precision of 1. What this means is that Haskell systems that have a similar distribution as the sample set will get a higher IVD score than systems with a deviating distribution. And the parameterized IVD function then looks graphically as follows. And the lower bound is chosen such that systems with a median lower than the sample set do not receive a disproportionate low score. In other words, the left slope is not too steep. And we have chosen to use the median to determine the ideal value because the median is resistant to outliers and can be easily calculated. As the median of the sample set is 69 log, the ideal value for module size is set to 69. Next, the lower bound is set to -50, so negative values are possible to prevent a disproportionate low score, and the upper bound is set to 269. Now, this ensures that a large part of the distribution is represented while still maintaining discriminative power up to 1 decimal precision. To validate the IVD function, we have randomly picked 15 systems from our sample set to calculate the IVD score. And this box plot shows the distribution of these 15 systems and the sample set for the module size metric. This line here depicts the median of the sample set, and each system's IVD score is shown here. We can see in this plot that systems with a similar distribution as the sample set, such as, for instance, Cabell, receive a progressive higher score than more deviating distributions, such as, for instance, ByteString. So, we can see that the IVD function behaves as intended. Concluding, we have parameterized the IVD function for module size, module cohesion, and module coupling. We have verified the IVD function by calculating the IVD scores of 15 Haskell systems and compare these scores with the system's distribution. So the result is that the IVD function can be used as a benchmark for Haskell systems. And in the following phase of our research, to ascertain whether structural degradation in Haskell systems is related to decreasing software quality, we have used the IVD function as a benchmark in combination with the inequality measure. The process for obtaining the dataset for this phase is very similar to the previous phase, so I won't go into detail. For this part, we have mined the source code repositories and the issue trackers of Cabal, GHC, and Pandoc. And these are all three popular open source Haskell projects with a relatively rich revision and issue tracking history. The dataset consists of the three metrics aggregated with the use of the Gini coefficients complement CG and the combination of the CG and IVD scores. It also contains the post-release defects of these three projects. And this enables us to measure the correlation between each of the 6 independent variables, which are the aggregated results and the dependent variable post-release defects. We have used 18 Cabal releases, 21 GHC releases, and 29 Pandoc releases. Our results show that there is a significant correlation in the inequality of the module size metric population and the post-release defects for all three systems. There is also a significant correlation for the module cohesion in Cabal and GHC, and we measure a correlation for module coupling, but only in GHC. Looking at the combination of the inequality measure and the IVD score, to see if the strength of the correlation with post-release defects have increased, our results show that the strength has increased for the module size of Cabal and the module coupling of Cabal and Pandoc. We did not see any increase for the module cohesion metric. So concluding, we only accept the first hypothesis that module inequality is related to post-release defects only for module size. We do not accept the second hypothesis. We are conservative with regards to conclusions that can be distilled from these results, and is mainly due to the small sample size. For this reason, we accept the hypothesis only if it holds for all three systems, as is the case for module size. What this means is that the inequality measure can be used as an indicator for the growing likelihood that coding errors appear when module size differences increase within a project, making it a useful system-level metric to monitor this aspect of the software quality. Finally, we have looked whether the inequality measure is useful as an indicator for large structural shifts. We have plotted the CG results per release to get a picture of the evolution of the three system-level metrics. What we want to know is if the inequality measure can point the developer to large structural shifts, so it can function as a trigger to investigate the exact nature and rationale of the change that caused this shift. We have set the threshold during our research at 4%. So for each shift equal to or larger than 4%, we performed a root cause analysis. And as an example here, we can see the evolution of the Cabal system. When we take the shift of -8% and -9% of respectively the log and CVO metric, and then look at the source code and revision history of that release, we find the version introduced 166 new modules. The decline of these values can be explained by the introduction of smaller, less coupled modules, while at the same time existing modules grew in size and coupling. So the inequality of the whole system increased. The -7 drop here is caused by the introduction of two modules with an exceptionally low cohesion. Another observation we made is that the inequality gradually increases. And this information could, for instance, be used to set an inequality threshold at which a specific refactoring session is started. For all these systems and metrics, we observe that there is always a significant amount of inequality, and it stays between certain bounds. This shows that for these three systems, developers seem to be comfortable with a certain amount of variations in these module characteristics. Concluding, we see that the inequality measure can serve as an indicator of structural shifts, and thereby we accept our third hypothesis. So, I've presented our work on researching methods to determine and monitor the software quality of Haskell systems, in particular the specific software quality aspects regarding the distribution of module size, cohesion, and coupling. And summarizing, we have parameterized the IVD function for the module size, coupling, and cohesion software quality attributes, so it can be used as a benchmark to evaluate Haskell systems. We have developed a method and software to analyze evolving Haskell systems, and we have shown that post-release defects are correlated with the inequality within the log metric population. And the inequality measure is able to reveal structural shifts in evolving Haskell source code. The software we have developed to analyze the Haskell source code is open source and publicly available. Finally, our paper can be downloaded at a given URL, and our research data is also publicly available. Our software is available through Hackage, so please take a look at it and try it out yourself. If you have any questions, please let us know.